Welcome. Can you all hear me? Okay, cool. My name is still Łukasz Langa. If you attended my yesterday's talk, I'm still from the internet, and this is still a Python talk. So that should be more aligned with what a C++ conference is all about, because it's, oh yeah, static typing is actually useful. So I guess I'm going to have a bit more of a understanding today than yesterday. So that's cool. Like, we're going to talk about how type annotations actually make production applications better, and how you can also add that to an existing application. You don't have to start over and write a new application with it. So first of all, we're going to actually have a nice introduction to how do static annotations even look like? How do type annotations work in Python? What's the syntax, what's available and what's not? It's going to be a very gentle introduction, so you should be able to sort of like, start from scratch if you haven't seen them at all yet. Then we're going to move to actually talking about, I already have a million lines of code. What do I do now? How do I make this work without, being crushed by 1,000 errors on day one? And finally, when we're already ready to actually introduce typing to our application, I'm going to share some experiences that I had from introducing typing to a pretty big code base of Instagram. So hopefully some of that is going to be useful also in your applications. So first of all, I don't think I have to ask this question in this audience, but you have to believe me that in the Python community, having type annotations is still a pretty controversial thing. Python is known to be this runnable pseudocode, like a very friendly language, like it's minimal syntax, reads like English. And when people see annotations, when they see types, they think, oh my God, it's going to be Java, or worse yet, it's going to be C++ with templates and all that insanity, like, in a year now, and what are you doing, Python developers? So we have to tell them, like, hey, relax. It is actually not to screw you over. It's to help you. It's to help you because you need to make sure that you understand the code that you're reading. The common example that we share when we talk about this is that function. What does this do? Well, it's still Python, still runnable pseudocode, reads like English, but can sort of do anything, right? We don't really know what items is. We hope it's iterable because we are iterating on it. But we need to sort of guess from context. We don't quite know what we're iterating on, especially that we're just calling some children attribute on it and then a process method on that. So is that children thing always set? We don't really know. What is it? We also don't really know. Like, we need to read code. We need to sort of like by a cyclomatic complexity, figure out like which are the paths in which that is set and where it's not. But what does the process method do? So you're like, dude, it's nice and easy. Grep's been around since the 70s. I'm just going to grep and it's going to find me the right function. And then you find out you have 300 separate process functions in your code base. So it wasn't actually that easy to find out like which is the one that we're going to execute at runtime. So here we are at the most important reason why we want type annotations. We want to understand what the hell is going on. All of the other reasons are secondary. This is the most important issue. Like, we want humans to be able to understand what the author meant. And that author might have been you 6 months ago, right? So that makes onboarding new team members way easier because they can just read like, oh, okay, I can pass a list here and whatnot, right? It makes code review easier because you don't have to then like open your editor and like, oh, you just made a change to this file, but the imports actually lead me to the depths of some unmaintained code later. Like, that makes that way easier. And finally, if you're actually debugging a thing, like, it's easier to see like, oh, those two things don't agree. So that's the first reason. Then we would have some assumptions that you as the author make when you create a function, right? So you, for example, never intended this to be like a, any iterable. You always want it to be a list. It just happens to work with other iterables, but you never meant it to. So if somebody actually is using it with something else, it just happens to work. You want to specify the assumptions that you yourself made explicitly, such that it's future-proof against unintentional API changes or against like sort of API abuse later on. Then like we don't really want to think about the entire program all at the same time, right? Like, you know, everybody knows the cliche about like just remembering 7 things plus minus 2, right? Like in your brain. And in fact, for complex problems, when you're actually trying to solve a problem, it's even less than this. So you want to have more space left in your brain for application logic and not have to unwind the dependency graph and, you know, see like where the types lead you. Like you don't want to have to think about it all the time, which actually leaves less room for mistakes. So that's important. And finally, at the very, you know, end of the reasons, we want to find existing bugs, you know, and prevent future ones with type checking. So all of those, as you can see, like type checking is just a sort of like a cherry on the top of the entire like typing cake. So how does that look like in Python? If you have a regular Python function, you can annotate the arguments and the return types like this. This is Python 3 syntax because you shouldn't use Python 2 anymore. In fact, like, yeah, you should really use Python 3. So 3.7 is coming out in June. There was a sprint like last September. I printed those t-shirts for it. So yeah, I digress. Anyhow, yeah, this is the syntax. Like there's argument types, there's return types. They are preserved at runtime. You can access them then, like if you need to for any reason. So they need to be valid Python expressions, right? People see those annotations and they often ask me like, hey, I have another idea. Like, why don't you use docstrings for this? Like, a lot of people do. You have Sphinx syntax. You have Doxygen syntax. You have all sorts of things that you can do. Like, PyCharm supports some sort of syntax for this. Well, we couldn't. We wanted to use docstrings like at very first, but we saw that they're outdated and wrong. So docstrings, like the thing that you're documenting your function with, is written by humans and not validated. It was never validated in the past. So that at best describes like what the author hopes is true, but it's very rarely even close to be true. And like, you know, and it's often not machine parsable because there are like some formatting issues there or whatnot. So couldn't use docstrings, had to be some other syntactic place. And if we're talking another syntactic place, then like, why not just assert things at runtime? That's like what Python is all about, right? Like accept everything and then maybe just check, you know, do is instance checks and like, you know, solve that problem right there, right then. Well, asserts, on the other hand, are overly restrictive. Python is all about duck typing, which means I don't care what type it is. If it has this method that I'm calling or this attribute that I need, it's all fine. So if you're just checking for a particular type, maybe you weren't quite looking forward enough to see that it's not just dict, it's also ordered dict or anything else. So that is actually not a very great idea to do. More importantly, that slows down runtime, which is already not perfect in Python. So why make it even worse? Is this Pythonic? People ask like Pythonic, right? Like what is this? So type annotations provide important documentation for how a unit of code is used, right? Programmers should provide those type hints as public APIs, you know, somewhere in the documentation or like, you know, in comments or whatever. So this kind of information that type hints hold has always been possible to somehow express, but there was just no standard for it. So because of this, and there's already like a number of formalized mini languages for it, people that are responsible programmers creating libraries for others to use already did that. That only moves the syntax in a way where it's standard and it's easy for everybody to read. So yeah, in that sense, it's totally Pythonic. There's nothing magic about it. So what can T be? What can R be? T can be any built-in type, like str, like int and whatnot. Can be collections, lists, whatnot. But can be any arbitrary type that you define. So if you define a class, you can use that class, like media type, which is one of the types in the Instagram code base. So yeah, that's it. And then you have the return type. And that's pretty much the same thing. One thing that I always like to point out is you can also say none. So if your function actually doesn't return anything, you would just say none. Technically, if you're like really this like, you know, very formal typing person, you're going to say, no, none is a singleton, and the type of that singleton is non-type. Yeah, but nobody wants to like import a thing from types just to be able to type this. So yeah, none is a singleton, so it's good enough for us. It reads very well. So that's it. Like if your function doesn't return anything, do none. Okay, enough of like dry examples. Let's look at actual code, right? So now it's going to be a bit controversial. So brace for impact. It's not going to be either VI or Emacs on the slide. It's going to be Adam. You should move too. I said it was going to be controversial. That's a very trivial example here, right? Like GCD, like everybody implemented that at some point. The type checker is happy. It's like no errors, everything is good, right? So if we did something wrong with the invocation of that greatest common denominator in line 7, for example, passing a string in the first argument, the type checker would say, oh, haha, you put a string, but you meant an integer. So you're like, okay, dude, big deal. If I ran this code, it would crash anyway. So what's the point? Like now my editor shows it, but Python would show me anyway. Yes, it would. It would show you a very intuitive error like this. Not all arguments converted during string formatting. Yes, because Python is a very dynamic language, and sometimes errors, you know, caused by wrong types happen very far from where you made the mistake. So, in fact, I think, that's my personal opinion, that it's way easier to understand the first error compared to the second one. Yes, you will finally debug the problem in the second problem as well, but it's going to take you way more time than just looking at a very obvious error message. So yes, if you have classes, the type checking can do the same thing for you. And again, like having those sorts of errors at runtime sometimes actually causes very unintuitive you know, messages. And in this case, very easy, right? Like you can see that point has no attribute z. And another thing that I wanted to show you is that type checking in Python has this magic function that you can use to figure out like, what is the type checker doing? What does it think that type is? It's called reveal type, and you can use it to see like, oh, okay, I see how that works, right? So there's sort of type inference there. We're gonna talk about this in a bit. So types are actually, yeah, they're classes, but they're more than just classes. So there's actually very many instances of things that aren't quite just simple classes, but you would use them as types. For example, right, if you want something that returns like any possible type in your application, and by the way, you don't have to like remember all this, we're gonna go through them one by one in a bit. If you want something that like accepts lists of strings or whatever else, so like generics, right? If you want to have multiple types that are accepted, you want to list them. If you want to have instances of either one type or maybe none, right? Or stuff like this. So there's many possible things that are technically types but aren't quite very simple classes. You can also use typing to express that. There is additional complexity here, since now you have to use the so-called typing module, right, that we provide to express any sort of like complex typing unit or like typing construct. Like any is the simplest one of it, and like again, some typing purist would say it's not any, it's some, right? Because it's only valid for some. For others, it's still going to fail. Yeah, but we call it any. So don't abuse any, because that pretty much tells the type checker that shut up. It can be anything, and you shouldn't report any error in any case. So you should use it in existing code bases if it's so dynamic that it's going to be super tedious for you to enumerate the possible types. That doesn't happen quite as often as you would think. For return types, that happens a bit more often than for arguments. We're going to talk about this later. So a value with the any type is essentially dynamically typed as far as the type checker goes. And the type checker is going to accept any attribute or any method that you try to call on an object of that type. Right. So lists and other collections in Python can hold arbitrary pieces of information, but usually collections like lists and dictionaries hold uniform content, right? So a list is going to be typically a list of string or a list of ints or whatever else. Unfortunately, there's no easy way in the Python syntax to say this, like to say, hi, I need a generic list for typing, which is why the module provides an uppercase list just for that typing purpose. So you can then say, you can use generics to say, I need a list of strings for this. And as well, like we provide the dict, we provide set, we provide mutable mapping or whatever else, like, all the ABCs, all of them live in the typing module. In the real world, you're going to find a lot of code where there's this magic none value that is also accepted. So you're going to have some string, but maybe you can also pass none there. So you would say optional of string, because it's either string or none. Again, you shouldn't quite abuse this if you're constructing a new function, because then you really have to figure out that in all the possible paths in this function, what do I do with this none? But in existing code, this is going to be pretty prevalent. People sort of implicitly assume that it can be maybe none. So optional string is how you would say this. This is how you should say this even if you have a default value of none. But historically, we allowed for people to just say it's a string but has a default value of none. In which way we would implicitly assume that it's optional because the default value is none, right? In practice, actually using typing for real projects, we found out that this is confusing. And people that are typing and they're looking at the type and not at the default value sometimes miss that it can be optional. And sometimes they don't understand that it's still optional and they say, why doesn't this generate an error? So this is likely going to be removed in Python 3.7 and you're going to get errors for that. But so far, yeah, that was one of the mistakes of PEP 484. So I have to share this with you that you might see this in production later. But use the first variant. Explicit is better than implicit, right? Should know better. Okay, if you have any of two types, and not necessarily just type and none, the generic variant of it is called union. So you can just say union of A or B, so either one or the other. That's pretty much it. That's pretty obvious what it does. In terms of returning the same thing that you received, you can use typevar to say, oh, I received a thing and I'm going to return exactly the same one. This is pretty nice of a syntax. Looks like generics because this is mostly what you're going to use it for. But sometimes this is actually useful for elements of a collection, and you can use it like this as well. You can say, I actually have a list of T and I'm going to return one of them, I don't know, the first one or the biggest one or whatever that means for our particular function. There are cases where we're going to have a type that we know that this is an int, but I don't mean any int. I mean those ints are specific. They're, for example, IDs in my database. So this sort of prevalent ID at Facebook is just called, not unsurprisingly, FBID. So we can say, okay, it's technically an int, but we actually want to constrain the usage of it to be that has to be an FBID. So we are going to use new type. So functions that accept FBID will be unhappy if you give it an arbitrary int. They have to now be compatible. You specify that you really mean this. You got an FBID from a database or something, and you for sure know that this is going to be valid for this particular use case. Type. Well, normally, if you are using types in arguments or return types, what that means is I want an object of this type, right? I want an instance of it. If you actually mean, I want a class, because, for example, I'm using a factory and I'm going to use this class to create new objects, then you have to say type of Django model, which literally means the argument is going to be a class. And that type means it's going to either be a Django model or any subclass of it, because that's still compatible, right? Like, you know, the list of substitute principle tells us, yeah, subclasses should be fine for this. I already showed you type vars, but sometimes the type var is not going to be enough. You have a T, but you're like, yes, I am going to return the same thing, but it has to be a Django model or its subclass. So you can bind type variables to a base type, which essentially means, yes, it's a type var, but it won't be valid unless it's a Django model or its subclass. All right, so pretty much these are the building blocks. But if we had to use them everywhere to type every variable and, you know, every attribute in every argument and everything everywhere, it would be super tedious. So we're doing type inference instead, right? You don't have to type everything, and the type checker will understand what is going on very often as well. For example, if you actually assign a thing, right, it will automatically infer that, oh, it is an int, right? Reveal type will tell you this. In case of a list, if that list is not empty, it will see like, oh, I guess it's a list of string. If you passed an empty list, or if you assigned none, then we don't really know. Yeah, here it is. Yes, for an empty list, like the type checker will tell you that you need to provide me an annotation so I know what you store in those lists. In terms of none, it will just assume, okay, it's none. But that's pretty useless for a variable if it can only hold a singleton, so that's probably not what you meant. More importantly, the type checker will complain if you are actually using like 2 types for a single variable in your function. So shadowing with incompatible types is a problem in Python, and the type checker is gonna yell at you. Names are almost free, so you should just use a new name if you really convert a type to something else. Because otherwise, you're gonna see a nicely annotated argument to a function, you're gonna assume it's a string, and then you found out it was actually converted to something else along the way, and possibly only just for a single path from all the possible paths in a function. So shadowing is gonna yell at you that you changed your mind midway on what this variable is. It's called static typing for a reason, like you should stick to one type for one variable. If we need generics, and we have collections, we can already infer that, okay, if this is a list of strings, then a single thing inside it is a string. So that is sort of provided for you, like it's what everybody expects, so it works correctly, right? So you don't have to additionally just say that, oh, I just got a string, because that would be very tedious. So most of the built-in collections already have this, and if not, like we're adding those types like to the annotations for this talent library as well. And yeah, and we can sometimes improve the inference by, you know, doing like guards and early exiting a function. For example, if you had something that was optional, you can still say like, oh, if it's none, then return. So the type checker will understand that, you know, below that early return has to be string. It cannot be none anymore because we returned if it were. So that is also very useful. Like, you know, if you're doing is instance or whatever, like it's not gonna yell at you for like, you need to tell me. No, you told me by using this instance or by exiting early. Variable annotations are available only on Python 3.6. I already told you should use the latest version possible. People make the mistake, don't do that mistake, of using whatever version the operating system ships with. That's not quite what you should do, because the version that is shipped with is mostly for internal use of that particular operating system. Very often it's a very outdated version, like Red Hat will ship with Python 2.7 for quite a while still. But you should know that Red Hat as well has supported packages for Python 3, and 3.6 is already in there. So there's software collections that it publishes. You have to install them for your particular use. So use the latest version. There's no reason why you would just stay for whatever you know, your particular distribution ships with. Even if it's some old version of Python 3, it's still like, why would you do that? At this point, you can use the latest. If you use the latest, you have variable annotations. So you can say, if you need it, this is nice, right? Like, this is a list of string or whatever else. In the old versions, you would have to use an ugly comment, right? You will need to say the type of this expression is list of string or whatnot. All right. When everything else fails, you can cast. It's not quite the same meaning as in C++ or anything else, but sometimes it's important. Like, for example, if you actually have an int from somewhere and you have to say, this is an FBID, trust me, you can do this. So you don't really use it that often, like you shouldn't. Like typically, your code can be trivially refactored not to require cast, but it's there because there are situations where there's no other way. All right, so we're done with the first part of the talk. Now let's move on to how do you actually create an application and then apply types after the fact, right? So if you already have like this, million lines of code or whatever it is for you, how do you actually provide value by gradually introducing typing information to it? So in a statically typed language, typing information must be complete, right? Like when you're starting out to even compile the thing. In a dynamically typed language like in Python, types actually don't matter at all because at runtime, we're just trying to access an attribute. We're just trying to execute a method and we're going to see what happens, right? So classes are like factories of objects and we just use whatever we got. So that's true for Python, that's true for Objective-C, that's true for Ruby. So unless runtime is instance checks are performed, like you don't really constrain typing at runtime at all. So that's the difference, and that's why gradual typing is necessary in our case. Okay, let's say we have functions. We have a project with functions. They're not files; they're like functions in your project. So gradual typing is all about introducing those type annotations in a way that like you function by function, increase coverage, and everything stays green. And if you make a mistake, it's red, but like you fix it. So everything gradually just shows that you're a competent programmer and like everybody is happy, right? And in fact, if done correctly, this is exactly what you're gonna do, right? So this is what we are doing at Instagram. So the graph doesn't quite go to where we started because I'm incompetent and I didn't quite do the metrics from day one. But when I started, yeah, we were like around 2.5% there. As you can see, like functions and lines, not quite there because it turns out that the functions that we are actually typing are the nice ones and they are actually pretty short, so cool. We actually have an additional metric for generated code, but it's useless because it's generated code, so nobody's going to type that, or maybe it's already all typed, so that doesn't matter. But currently, we are, what is it, over 22.5%, almost 25. Wow, that's pretty cool. So that is definitely possible. It's not quite as easy as it looks from a nice graph that goes like this, but we're going to show you like how you can avoid some of the problems that gradual typing actually has. So let's say, before we type the first function, what do you expect the type checker to tell you? Well, you would expect it to say that there's no type errors, right? You would say, you would expect it to say, I guess it's fine. You're running in the production, so I don't know, like who am I to judge? And this is close to being true because with gradual typing, if a function is not annotated, we cannot really infer what's inside. Like there are projects that try, but that is very noisy. So like the pip484 type checkers like are just going to totally ignore functions that are not annotated. You need to understand that Python is a very, very simple language like that sort of started out from scripts. So there's also computation on the module level, right? Like when you're creating your classes, when you're assigning globals or like stuff like this. So you can still see errors when nothing is annotated because there's already some issues on your module level. But that's typically a very small amount of things unless you do crazy things on module level. Like you should see like maybe a bit of those. So you should expect the slate to be totally clean. And then you type your first function, right? So in this situation, the type checker will only be able to look inside that particular function. Is that useful at all? It is, because if you are doing like logic errors inside, right, or actually not agreeing your implementation to the arguments that you said you are actually specifying, or you're returning something else than that you declared that you're going to return, that's already going to be useful. And better yet, we provide annotations for the standard library. So if you have standard library use, we can also help you if you use the APIs there in a wrong way. So that's already useful just a little bit. But the important thing is that by annotating this function A, function 0, like the first function in your program, you are enabling annotation of another group of functions. For those guys, if you annotate those, then it will check if you're internally consistent, if the standard library API usage is matching, and if the usage of our function 0 is correct. Right? So this is the power of gradual typing, that by typing those guys, you're going to be like green, green. Oh, I actually used my function 0 in a wrong way. So then you can fix those usages, and like your code gradually becomes better. So there's definitely a cliff of seeing how gradual typing is useful. When you're going to first start out, you're going to just see it as like an academic exercise that you're doing. It's like, okay, now I feel almost like a Haskell programmer, right? It's awesome. But later on, suddenly you're going to see like, oh, this thing caught so many errors that we have elsewhere. So there's definitely some ramp up that you have to do. To show you how that works in practice, let's see this like stupid piece of code. The type checker is fine with it, right? Even though it's totally wrong, because you didn't annotate any functions. So the type checker is like, what do I know? Before we annotate the first function, no type errors are reported. When we do the first annotation, it already can tell us like, hey man, lists have a sort method. That's true, but that method doesn't return anything. So apply yourself. You meant sorted, I guess, right? Like the sort method sorts in place. It doesn't return anything. So you're like, oh, that thing is useful. Told me that I'm being incompetent. That's great. So that already finds some errors, but there's a lot more there. And we're not actually finding those yet. Even though you already can see that there's like something not quite right happening above us. So let's say we actually annotate another one, like annotating process all alone doesn't find the issue with its use of process strings below. If you see like the types don't quite match there, because process strings itself is not annotated yet, right? So it's like we annotated, but that didn't win us much. When annotating process strings, however, like we already see like, oh, there's a lot of errors reported. And actually, most of those are on line 4 alone, right? There's like, you returned a thing, but we didn't expect anything to be returned. Argument 1 is wrong. Argument 2 is wrong. Like, you know, everything is wrong. So if you can see like the out of order annotation can sometimes reveal errors later on in the process. By annotating process strings, we revealed errors in process all. That suggests that the order of annotating things sort of matters for like your ergonomics of like type annotating your project, of gradual typing. So to show you this on a nice graph, like let's assume that like we have this function that we're annotating first, right? Again, before we annotated it, like the type checker sort of doesn't show you anything. When we annotate the first one, the type checker will be able to find very few errors. You're going to fix those. It's green. Then we can annotate those others. So we expect like that everything is going to be great, right? Like we expect that it's all going to be, you know, nice, and then we can actually fix errors once they appear, and we're going to move on. But what if we actually didn't annotate that first function? The order would be different. We would start with those dark green ones. In this case, at first, the type checker would be like, everything is good, everything is great. And then suddenly one day, somebody comes in and annotates function 1, and then the type checker fails for those other annotated functions. So that happens relatively often. It's like, by annotating a thing and having the type checker clean, you don't quite are able to prove that my function is okay. No, it's gradual typing. Like by annotating all the usages of functions that you have, like, you know, you must have that that function annotated first to be able to say that I am golden, I am good. So the first suggestion from me is that you should find the most critical functions and start with those first. That's typically easy. It's like if you have a database that you're accessing, annotate the APIs for that first. If you have some utility functions that everybody is using, annotate those first. And like very often you can pretty clearly see like from like your code, like which is the actual library in your part and which is the leaf business logic that doesn't matter that much. And also what I would say is enable a file level linter type checking early. So if you use PyCharm or Flake8 MyPy, which is like a plugin for Atom and Vim and Emacs or whatever, you're going to see just type errors from a given file. It's going to read it from top to bottom, and it's going to show you errors that are constrained to that particular file and the standard library and some third parties. So that way the coverage goes up steadily because you're already like, you know, providing value when you're creating new functions, right? If you're like thinking and using logic, applying logic to my presentation, you're going to say, dude, you just contradicted yourself. First, you said that you need to nicely figure out the important functions first, and now you're saying, do the file level importing, even though it doesn't look at the entire program yet. But in fact, very often people create new files, and they write new functions. So for those, like just having annotations is already very useful, and you know, covering core dependencies quite at the same time or maybe a bit later, it's not a very big deal. Like, you know, if you even create an issue because a core dependency was covered a bit later, the guy that wrote the function or the lady that wrote the function, like, they're going to still have it sort of in fresh memory because that was a new thing. However, if you're annotating something that is like a year old or 2 years old, then you better be sure that like that thing is annotated once and for all, because you don't want to be this guy that is called all the time like for errors in that function because you were just that person that added annotations to it. But in fact, in real life, like it's not as easy as just file level. We have one file and we're golden. You have like this crazy tree of dependencies, you know, one thing imports another and that another thing imports another. And sometimes one module is imported from multiple places, you know, like, yeah, this crazy graph, like you, by the way, don't need to read it. It's just an image. But when you have the full program analysis, suddenly the problem becomes much harder for a type checker like to do. So the type checker that we're using in Python, called MyPy, does all this, but it's slow. So you cannot quite like use it as a linter in your editor to just show you errors like at the time that you're typing. Not quite yet, because for example on the Instagram code base, it takes around like 40 to 50 seconds to run over the entire code base and say, hey, you have errors here and here. So yes, we're working on the performance of it, but so far this is where we are. So what we can use it for is like as a sort of a continuous integration unit test, right? But MyPy performs full program analysis, so far it's slow. When it cannot find an import, that depends on the configuration. You can either ignore the error, in which case it's just going to assume any is everywhere that I don't know about, or you can actually configure it in a way where it will say, any import that I don't know about is an error, it's invalid. So that depends on you. Like with gradual typing, it sort of probably makes more sense at first to assume that anything I don't know about is okay. Otherwise, production would break. So I guess it's really just, we have some crazy dependency from somewhere else in production. We just don't have access to that source code yet. Yeah, so sometimes when you do this, that you are assuming any for things that you don't know about, that will hide usage errors. Like imported classes are functions, and functions are treated as any. That's what you sort of what you need to deal with gradual typing. And then like Flake8 MyPy and PyCharm are like simpler there. PyCharm still tries to do full program analysis, but it is this sort of editor, you know, like IntelliSense feature, so it has to be very quick. And at times, it'll cut corners because it really needs to respond very quickly to you. So again, what if some of the functions that you're typing don't really come from your code base? We just talk about this with MyPy. Like sometimes it's not your code. It's, I don't know, requests or click or whatever else that is either a third-party project that is not annotated itself, or maybe it's not even Python. It's a C extension written in C++ or Rust or whatever else, and you just import it and it magically works. But there is no Python code to actually do this. Like, that actually creates this sort of gap that you cannot easily fix by annotating it yourself. You shouldn't be expected to, even if that's Python code. Like, you don't want to go like and harass like Kenneth Rates or Armin Ronecker to like annotate their libraries. Well, I would encourage you to, but you might not be very successful there. So what you should be doing instead is write stub files. There is a special feature of typing called stub files. They have this extension called PYI. Technically, they're still Python syntax files, right? But they don't have the implementation of everything. They only hold like stubs of the interface. It's a C++ conference, but don't call them header files. They're not meant to be header files. They're just like stubbing out things that are outside of your control. For example, that's part of the requests, you know, types that we actually defined. Some of them are really crazy, right? But like, yes, like if we provide them for you, we're gonna actually take our time to do some crazy typing so that actually this is very useful and it's gonna show you all the errors. If you were really just like a user, like you would probably stop at this union that starts in line 12 and ends like 6 lines later. Well, yeah, but PYI files, super useful because external annotations can be then applied to sources that we don't want or cannot annotate. So we have a collection of all of those for the standard library, and we add third-party libraries to it too. It's called TypeShed. It's on GitHub, and MyPy and PyCharm and a few other tools are actually using that already. So it's shared across multiple implementations of type checking. So that's a pretty nice accomplishment that by sharing the syntax and the behavior, we were able to just agree on one set of annotations for multiple projects. So continuous integration. You should enable it because you would be surprised how fast people are screwing themselves over and, you know, introduce changes in the code base that aren't compatible with what you're doing. So this enables full MyPy checks, and this will actually catch like all the nice, like, you know, misuse that you or somebody else did in your project. And if you already have unit tests that have to pass and whatever, and you do this concurrently as a check, you are not really making the build times and the integration times any longer. So I would encourage you to do this. It's definitely fast enough for this use case, so you should do that. Yeah, but also you should totally provide a command that people can trivially invoke locally from their box, from their laptop, or however you're developing, so that they can check whether the error is still there. Because the functionality of just blindly fix some types and then upload again and see if it fails, like that's gonna generate some pushback. So you need to have a nice way to tell people, oh, there's a type error there. To fix it, try this, and you know, you can do that locally. So yeah, gradual typing. To sum up, only annotated functions are type checked. A clean run of a type checker is no proof that we're good. It can still be pretty buggy, but because of gradual typing, we don't have the full picture yet. New annotations can discover errors in functions that you annotated before. So the ordering here is pretty important. And some of the plugins like Flake8 MyPy only present type errors related to the file you're looking at, because the focus there is performance rather than completeness. And a full code-based check is why you're here for. Like, you should totally do it. Continuous integration is how you would do it. But how do you know that you won? What does success mean, right? Like if you're actually like meeting your goals or not. Like everybody wants to get a medal. Like, how do you measure? you can do multiple things. Like the coverage that I showed you before is the simplest thing that you can do. You can also like look at your logs like Sentry or whatever else your application is using and correlate whether the growth of your coverage in typing is decreasing the amount of type errors and attribute errors that you're seeing in production. In fact, this is not so easy to see as I would like. So there's a lot of fluctuation in like the code base, anyhow, right? Like Instagram is deploying 50 times per day. Like, so there's so many changes that that is still pretty noisy, but you're gonna see some general trend. Like most likely, this was surprising to me. You're not gonna see a nice decrease, like the correlation is not going to look like this. You're going to see that if you looked very far in the past, you would see a steady rise of shittiness in your code base and like with the number of errors at runtime. And that is going to be gradually slowed down by the introduction of type checking, which sort of suggests that it's more about the new functions being better than the old ones. But that's still useful. But as I said, that's the fourth reason why we're doing type checking. The first three are more related to the developer experience, and you can just, gather feedback from new team members or just cover how much time you spend on bootcamping people a year ago versus now. And this is pretty clear. And Facebook is doing type checking for its PHP variant called Hack and for JavaScript with Flow. And it's pretty consistent across the board that once you're introducing types to a code base, like people are, more likely to be successfully onboarded in shorter time. So that's the second part. Now let's talk about gotchas that you're gonna fall into. I don't know about you, but I did when we actually tried our thing in practice. So I already told you that multiple times now, right? That only annotated functions are typed. But you're still going to sometimes be surprised by this. Like you can actually do reveal type on a function that is not annotated, and MyPy is going to tell you something. It's going to tell you, yeah, any. And you're like, why any? You're dumb. There's GCD is annotated. What are you talking about? Well, F is not annotated. So from this perspective, it doesn't know. So every now and then, this is going to be confusing. And sometimes that actually hides production errors, if you don't do that quite right? So only annotated functions are type, which means if you convert to string, that thing is not annotated, you just hit an error. So bear that in mind. Gradual typing, we are not Rust. We're not even close. Unions. People are thinking, unions are awesome because I can say I accept this or this, which means I now accept more. That's not true. You're accepting more, but you're limiting what you can use internally in your function. What it means is if there is one path, in which case one of the types is not going to work, or the other, the type checker is going to yell at you. For example, in this case, you're going to see that some element of that union doesn't have the lower method, and another doesn't have the bit length method. So sometimes that is fine, oh, these are bugs, I need to fix them. But other times it's oh, the other type from the union is actually so rare to be there that probably I should just tell people not to use it. I should reject it so that my code stays clean, stays simple. So this is up to you. How you should fix your type errors might either be by introducing more paths in your code, or by saying, oh, this API was overly optimistic. I need to constrain it. But unions limit allowed behavior. They are mostly tricky when you're returning things. So when you're returning things, you're like, yeah, I'm going to either return one or the other, right? Because that depends on what I'm doing internally. But that also means that the users of your code now have to know which is which, and they need to do an instance check every time for the type checker, because otherwise there might be an error, right? So again, sometimes you actually are like, good point, I need to fix this and introduce more paths in my code. But sometimes you're like, bytes, I actually only do that in this particular debugging scenario where this optional argument is put and like this configuration thing is flipped. Maybe you should say, no, I should just use a different function in this case, and I should simplify my API. So unions constrain behavior. And if you actually have historical functions that you're not quite ready to refactor yet, and you have the situation, the sad world of gradual typing would suggest you to use any, just to say, I don't really know. No, I cannot say union, because then all users of my function are going to be, sort of hit with this all the time. But if you're making new functions, always, think when you're returning unions. Out of order definitions. So Python is a very simple language. It was scripts, right? So it reads from top to bottom. So if you're creating a class, and then you're creating another class, you cannot use the type of the class that didn't appear in the file yet, because it's not in the namespace yet. It wasn't defined yet. So for this, you have to use this ugly string. You have to say, yeah, B, it's going to be valid at some point. It's OK. But because it reads from top to bottom when you're importing the module, you have to use this workaround. That bugged me. That bugged me like a lot, because that just looks ugly. That just looks like typing is this bolt-on, like half-finished thing to Python. So I'm like, no, we need to fix this. You need to fix this, and I wrote a PEP. And in Python 3.7, like, if you do this future import, like, this is going to work for you in annotations. So yeah, like, again, use the latest Python available. That's coming in June. Do it. Sometimes the out-of-order definitions are not about, like, the order in the file, but are about import cycles. So sometimes you cannot import a type for use in your annotations, because that would create an import cycle, and then nothing works at runtime. That's not what you wanted. So what typing provides is this special type checking flag that you can use to say that I'm only importing this for types. That is like doubly ugly, right? Because now you're like importing like type checking to say if type checking, then you only imported that in a way that is not available at runtime. So you have to use the stupid string again. So all of this is bad enough. And then like you use a linter, and the linter yells at you that this import is not used. So you're like, oh, this is just all bad, right? So again, probably you can tell like that bugged me. So in Python 3.7, that goes away, right? First of all, like underscore typing is a thing in Python now. You don't have to import anything. Like this is going to be like provided for you. And second of all, again, forward references work. So you can just do that, and it's going to do the correct thing. Mutable collections. What is wrong with this code? So most people, including me like a year ago, would say, yeah, that sounds like everything is OK, right? I have the function G, which accepts a list of string. So obviously, I can pass it to a function that accepts a list of optional strings, right? If my list only happens to have strings, it is for sure compatible with a list of optional strings, right? No, it's not. It's not because if you would be mutating that list in function f, now that type is no longer a valid list of strings. Possibly you put a new none value in function f. So function g now has a corrupted type. So MyPy is going to yell at you. It's going to say, no, you cannot do this. And most of the time, you're going to say, you're right, MyPy. I should revisit my life choices. But every now and again, you're going to be like, no, MyPy, I'm not changing this. I'm just iterating over it or indexing it or whatever. In which case, you should use one of the abstract base classes like iterable or like any other thing that applies to you that is immutable. In which case, MyPy is like, oh, that's immutable. That's fine. If you're not changing it, then it's compatible. Then like we have covariance in it. Crazy ideas. I'm very bad at this. Like at some point, I named all of those things that we're hearing now as like, that will never happen. And all of those things, like to spoil you, are happening. So yeah, like static type inference. Like I thought that, no, this is too difficult to implement. I'm going to do this because there's always dynamic central code that obstructs type information everywhere. But in fact, Google has a project called PyType, and it's very successful in like recovering types just by looking at what are the methods that you are calling, like what are you doing here. So that's pretty cool. They are doing static type analysis. You can use their PyType project, which is on GitHub. You try to use that. Runtime type inference. Again, I'm like, yeah, sounds awesome, but what if you have a union of 20 types? This is going to be a useful type. Or what if your usage is very limited and you're not going to actually provide the valid signature for a function? Like, so like runtime type inference is going to slow things down too much. Again, not true. Like Instagram is doing this, and that was a big part of why our graph looks as nice as it does. And there's a nice project like by Ethan Smith, which uses some feature of Python 3.6 that makes it actually pretty quick to gather those types at runtime. So you're not slowing down as much as you would think. It's sort of not unlike profiling in 3.6 up. So the slowdown is acceptable, especially in the times of unit testing. Like you can just turn it on then. Even in the sense of like, aren't we just applying, our types to a small subset of the application that just happens to be hit? In practice, turns out that is pretty comprehensive. Like sometimes you're going to see that there's going to be an optional value that the runtime inference is going to always say that is always none. The type of this argument is always none. That probably means that this optional argument was never used, and that's okay. Runtime type checking. There's multiple projects on GitHub that try that now. You can do that. Duck typing plus type checking. There's a PEP that I co-wrote with Ivan Levski, which is addressing this. So we can marry those two concepts now pretty nicely, which is cool. And finally, can we do performance optimizations from the types that we got? That wasn't even like in one of the goals for the PEP. But it turns out that with ahead of time compilation, which Cython proves, you can use our typing to make optimizations for it. So yeah, to answer your questions that you probably had, like all those things are possible and we're into them, but it's going to probably take some time until they're like super production grade and they're of the quality that you would expect to use them just as a turnkey solution. So should get support. There's many ways in which you can do that. Like that's pretty much it. Like there's a very helpful typing Gitter. There's the typing issues tracker on GitHub, and there's a MyPy issues tracker for stuff that you have. So reach out to us. Make sure that like you're being heard. It's an early stage project, and every now and then you're actually going to find a problem, and we're happy to help you fix it. The slides are available. That was typing production applications. Thank you very much.
Maybe one question. We have not so much time. Maybe one question.
And if there is any deprecation mechanism, I mean, what if someone would like to change his type from int to FBID type,
yes.
And at the bottom level in his module, which our customers use around, and we want to let them know that, hey guys, change this type because after a few months.
Yes. This is a great question. So in fact, Python has this functionality of the warnings module, which can generate deprecations. So what you would do is you would actually use a union in your argument. And that, as I said, like that union limits what you can do. But then you do the instance check. And in this instance check, you like emit the deprecation warning and convert to the type that you wanted, or like do whatever else, invoke a different function. Like that depends on you. So the type checker will understand that, oh, like I did the instance check, so the types are fine. So you're going to actually like create that like path at runtime, but that's what you have to do. Like you have to emit those deprecations somehow. And in Python, this is one of the things that we still do at runtime.
Okay, thanks.
Okay, many thanks, Łukasz, for the great presentation.
Thank you.
And now everybody runs the applause for the speaker.